This is notes 2.1, limits, rates of change, and tangent lines. In this set of notes, we are going to be able to talk about the displacement net change and the average velocity slash slope of a secant line. And then we should be able to estimate the instantaneous velocity, rate of change, and slope of the tangent line using a table of values or a graph. So first thing I want to talk about is displacement. In calculus, we often use either an S or an X to represent position. So displacement is the change in your position, and the order of that matters. So when I'm talking about the change in position, it's always going to be my ending position minus my starting position. Or if we're just talking about two different time intervals, let's say it would be the position at time 2 minus the position at time 1. Then for rates of change, some examples of rates of change would be like a velocity. That would be the change in position with respect to time. So I would be able to represent that as change of s over change of t. So any sort of rate will have a change of something over a change in something else. An infection rate of an epidemic, so that could be newly infected individuals per month. Inflation rate, the change in consumer price per year. Change in atmospheric temperature with respect to altitude. So when we're talking about the change in something over the change in something else, we should be thinking slope. So rate of change, I want you to automatically start thinking slope. Now, since velocity is one of our most common examples of rates of change, I want to talk about that vocabulary a little bit here. So speed, that is just the absolute value of velocity at any given point. So speed is not directional. It doesn't matter if I'm traveling forwards or backwards. My speed is just the rate that I'm going at that point. So that would be like 20 miles per hour going west would just be, my speed would just be 20 miles per hour. Velocity would be, assuming west is negative since it's going to the left, my velocity would be negative 20 miles per hour. So velocity is directional with its sign. Speed is just the value of that velocity without the sign. Direction, I kind of already spoke about that a little bit, but for direction, when we are moving forwards or up, so forward motion or upward motion, you have positive velocity. And then backwards or down, that would be negative velocity. I'm just going to say backwards because that could be up or left. I'm sorry, down or left. Whoops. And while I'm at it, before I get to drawing a visual for speed, I will write myself a little note, but that is just how fast an object is moving. All right, so I'm going to draw a velocity graph. It's a pretty basic one. I'm not going to go too crazy here. So I'm going to draw this first, and then I'll talk about each section. All right. So I want to interpret each section that I have going on here. So this first section, my velocity is negative. So when my velocity is negative, that means I'm moving backwards. I'm gonna add a little bit of space. All right, a lot of space, but that's fine. So like I said, this is moving backwards since my velocity is negative. However, because my velocity is the same at this point as it is at this point as it is at this point, it means that I'm going the same speed. I'm going a constant speed. So I'm not speeding up or slowing down. My next section, I think I'll highlight that in red, so I'll just go back and forth. My next section, I am still moving backwards because my velocities are negative. However, my velocity here might be like -5. This might be like -2, -1, 0. So my velocities are getting smaller and smaller. Well, I shouldn't say smaller. My velocities are growing closer to 0. So that tells me that my particle or my object is slowing down. So when we're talking about speeding up or slowing down in terms of velocity, you need to think about your velocity getting closer to 0 or getting more away from 0. All right, this section here, my velocities are positive, so that means I'm moving forward. And then whether I'm speeding up, slowing down, or staying at a constant speed, if I think about it, I'm going from 0 to bigger and bigger velocities, so my particle is speeding up. I want you to go ahead and pause the video, and I want you to label what is happening in each section for the rest of the video. Or not for the rest of the video, for the rest of the graph. So we have 3 more sections. I want you to say whether we're moving forwards or backwards, and then whether the particle is slowing up or slowing down, speeding up, or going at a constant speed. Okay, so my next section, velocity is positive, so we are moving forward. The velocities are also staying at a constant speed because I'm not changing my velocity at any given point in that interval. Those are all both the same positive value. Next section, velocities are all positive, so I am moving forward. But I am doing that while slowing down. I'm starting at a velocity of maybe like 5 and then getting closer and closer to a velocity of 0. Last section, my velocities are negative, so I am moving backwards. And then, let's see, we're at a velocity of 0 and moving away at bigger and bigger negative velocities, so I am speeding up. So remember, speed is the absolute value of velocity. So when I say speeding up versus slowing down, we're talking about just the speed itself. So non-signed velocity. All right. So let's go ahead and move to the next page, and we are going to talk about average velocity and instantaneous velocity. So average velocity is the change in position or displacement over a time interval. We always need to specify the time interval. So if I say average velocity, which you can abbreviate to AVG if you would like, over, let's just call it time 1 to time 2. Included because we're actually talking about those times and positions. So average velocity is the change in position over the change in time. So that would be the position at time 2 minus the position at time 1 over time 2 minus time 1. Now I'm talking about rates of change. I'm talking about slope. So the average velocity will measure the slope of the line that connects those two positions. So I have that here, and I'm going to draw the line that connects them. Now I'm going to cheat. I'm just going to use a straight line from, oh, that's really thick. A little bit thinner. Yeah, so I'm just going to use a straight line from my Promethean. Go. Better. Okay. Do you know what kind of line that is? A line that connects 2 points from your graph is called a secant line. So the average velocity measures the slope of the line that is secant to the position graph over a set time interval. So the slope of this line will provide me the average velocity, since it's a position graph, over the time interval that's provided on the x-axis, so time 1 to time 2. Now let's talk about instantaneous rates of change. So instantaneous velocity being a type of rate of change, we talked about different various ones on the front, is the velocity at any given moment. So visually, instantaneous velocity will measure the slope of the line at a single point. Does anyone know what the slope of the line at a single, or what the line at a single point is called? I'll draw one the best that I can. It should be a line that just barely skims the point that you are interested in on your position graph. So I would just barely skim, touch the graph, and then I'm not touching the graph anymore there. It's not the best tangent line. In fact, I might try one more time. That looks a little bit more on point. There we go. I like that better. So that is called a tangent line. So instantaneous velocity measures the slope of the line tangent to the position graph at a specific time. So if I ever ask you, how do you visualize average rate of change? You should tell me the slope of the secant line. If I ever tell you to tell me the visualization of instantaneous rate of change, you need to tell me slope of the tangent line. These are major concepts for this first semester in calculus. So next, when we want to estimate the instantaneous velocity, because if you look at that graph, I just eyeballed my tangent line. Your tangent line might have looked slightly different. So right now we only have the skills to estimate this instantaneous velocity. When we get into chapter 3, we will learn how to get the exact instantaneous velocity, but for now we need to work on estimating. So in estimating the instantaneous velocity, we will use the slope of a secant line over a time interval that includes the specified time. So we'll just say a small interval, because we do want it to be a very small interval, including the time that we have. Now, there are various intervals that you can use, but you want them to ideally be small and include the time. So maybe I would choose a small window from here to here. So that would be my secant line that I choose. It looks very close to the slope of the tangent line that I have over in this graph over here. So ideally, the smaller the interval, the better your estimate will be. So let's move on to example 1. The function s of t equals 4.9t squared measures the position s of an object in meters over time in seconds. What is the displacement of the object over the interval 1.5 to 2.5? So remember, displacement is the change in position. and you want to do your second time minus your starting time. So we'll do the position at 2.5 minus the position at 1.5. Whenever you are given a function, you need to use it. So even if I had a graph off to the side, you want to use the graph to guess values, use your function to actually get exact values. So I want you to pause the video. I want you to do this. Make sure you label your answer. And I am going to pull up Desmos and do that. And you'll see that here in a second. Okay, so I wanted to show you that you could use function notation in Desmos. So on your paper, hopefully I see 30.625 minus 11.025, and then that result being 19.6. Let's see what you are getting as your answers with your label. So we're talking about displacement, that's the change in your position. So we would label our answer with whatever the position's labeled in, which is meters. Part B says to find the average velocity over those time intervals. So we will do average velocity over 1.5 to 2.5. Remember, that would be the change in position over the change in time. So we're looking at S of 2.5 minus S of 1.5 over 2.5 minus 1.5. You'll do a similar thing for the next interval. Luckily, we already calculated this displacement in part A, so I know the numerator is going to be 19.6. And the denominator, well, 2.5 minus 1.5 is 1. So our answer is 19.6 what? If you are ever unsure of your label, think about what the label is for each part of this. So the label for change in position, meters. The label for change in time, S. So this would be 19.6 meters per second. Go ahead and do the average velocity for the next time interval, and you will see the solution pop up here in 3, 2, 1. There we have it. 29.4 meters per second is the average velocity over the time interval from 2.5 to 3.5 seconds. Part C, which of the average velocities from part B is a better estimate of the instantaneous velocity at time t equals 2, and why? The answer for why is very, very basic. So I would like you to try your hand at this question, and I'm going to go over the answer now. So the better average velocity for the estimate of the instantaneous velocity at time t equals 2 would be 19.6 meters per second. And that is because the interval from 1.5 to 2.5 includes time t equals 2, whereas the interval for 2.5 to 3 does not. That's it. Very basic explanation. So I'm actually just going to go type this up, and I'll have that answer up on the board or up on the screen now. So you can pause the video and write that statement down if you need to. Next example is that 2? Yes. A car is driven on a straight road, and the distance traveled by the car after time t equals 0 is given by a quadratic function s, where s is measured in feet and t is measured in seconds over the time interval from 0 to 12. Of the following, which gives the best estimate of the velocity of the car in feet per second at time t equals 6? So even when it doesn't tell you average versus instantaneous, when it gives you a singular time, that tells you what kind of velocity it is. So if I were to have an interval, that would be average. If I have a singular time, that means instantaneous. Also, there was a key word in the sentence that tells me it was instantaneous. I was looking at estimating, and right now all we have are the best skills to estimate instantaneous rate of change. So I want you to go ahead and answer this question. So your best answer should be D. And here's why. This, for answer A, just tells me the position at time 6. This doesn't represent anything. The position at a time divided by that time doesn't represent anything. This question here tells me the change in position over the change in time, which means I'm looking at an average velocity. However, the best estimate is going to include 6. They both do, but I want the smallest interval. 4 to 8 includes 6, but that's over a time span of 4 seconds. 5 to 7 is a shorter time span, and that shorter time span would give me the best estimate for my instantaneous velocity at 6. So we're going with this because it's a smaller interval that contains 6. And this question is straight from AP Classroom. You will definitely see similar questions to this on the AP exam. All right. Example 3. The figure shows the estimated number of internet users in Chile based on data from the United Nations Statistics Division. In part A, it says estimate the rate of change at t equals 2003.5. So when it says just one time, what kind of rate of change are we looking at? I guess we'll answer part B first. So is this asking for instantaneous rate of change or average rate of change? We should be saying instantaneous rate of change. You can abbreviate rate of change with ROC. I know it's a lot of writing. How do we know? Hopefully you're saying because it gives us just one time instead of a range. And then how are we going to figure out this problem? So how would I calculate the instantaneous rate of change? At this point, we just have to estimate it. Now I have a pretty visual there. How do we visualize the instantaneous rate of change? Hopefully you said we visualize that using the slope of the tangent line. So we want to get the slope of the tangent line. Let's see. I'm going to say calculate using the slope of the tangent line. If the tangent line was not already provided to you on that graph, you would need to get some pieces of information for an interval around 2003.5. So maybe you get the slope of the secant line from 2003 to 2005, or no, 2003 to 2004, since that's the smallest time interval that we could use from our graph. But we have a tangent line. We're just going to find the slope of the tangent line using points on the tangent line. So I would like us all to try to use definitely 2001, since that has like a y-intercept that is a clear point. It's not the most clear point, but I don't have to like guesstimate here. And then let's also use 2005. So the times are going to go on the bottom, 2005 minus 2003. And then in the numerator, we want the outputs at those times. So for 2005, what does it look like the number of internet users are? To me, it looks like it's just slightly above 4.5. So maybe it's not too far above. So maybe I would say like 4.55. Minus, and then at 2003, we're at 3.5 here, and then that's 4. So like 4.75 is here. It's really not too far past 3.5, so I think I might go with 3.55 again. So that would be basically 1 over the number of years 2. And our label for that would be, well, do we need to write that up in a sentence? No, we don't. It just says estimate. So our label for that would be the label for the numerator being the change in the number of users. So that would be internet users in millions, or I would say millions of internet users. So 1 million internet users. I'm not going to say in Chile. Per, and then this is representing time in years, so it would be per year. So 500,000 internet users per year is the instantaneous rate of change at 2003.5. Part C, does that rate of change increase or decrease as time increases? So if you want to know if a rate is increasing or decreasing, you need to think about rate of change being slope. So is the slope increasing or decreasing over time? So we already have one tangent line. I can think about drawing a tangent line here. I can think about drawing a tangent line here. So as I draw my tangent lines over the course of time, and here's that tangent line that was provided to us, does it look like the slopes of those tangent lines are increasing or decreasing? To me, it looks like those slopes are decreasing. So we would say decreasing because the slope of the tangent lines, which represent the rates, are getting smaller over time. Or you can say getting closer to 0. Part D, let R be the rate of change over the interval from 2001 to 2000 until 2005. Compute R, and then is this instantaneous or average rate of change? So I want to answer that question first. Is this rate of change that we're going to compute instantaneous or average? Hopefully you said average rate of change. Why? Because we have a time interval. Interval. So for the average rate of change over 2001 from 2000 until 2005, because we are estimating it, we should probably have a squiggly equal sign, which I should also have in question 1A. Well, I guess we estimated that, so that's implied. Never mind. So I want you to go ahead and do that. I'm going to put the values that I think we see roughly around 2005 and 2001 on my screen. They might not be 100% what you have, but if we are within, I don't know, maybe let's say one or two decimals of each other, I think we're going to be good. So I'll put my answer up here now. So keep in mind, this would be the slope of the secant line that connects these 2 points on the graph itself. So I'm looking at, let's see, can I draw that? Oops. The actual number of users here and the actual number of users here. So I went with 4.45 here since it's slightly under this line, and 3.1 since 3 would be at the bottom here. If you had something within like a small range of these two values, that's fine. My final average rate of change was 0.3375 million internet users per year. Do not forget your labels when you are doing word problems. And then lastly, it says, is the rate of change at 2002? So instantaneous. In fact, the visual for that would be drawing a tangent line here. So is that rate of change greater than or less than R? So let's think about visualizing the tangent line here, and then R is average, so we want to look at the secant line there. So I'm going to have to erase some stuff from my graph. So at 2002, if I were to draw a tangent line, I'll try my best. Yeah, that's good enough. Make that go red. I change that to be red. I can. Versus the secant line that connects 2001 to 2005. So I think just barely it looks like the secant line at 2002 is a tiny bit steeper than the secant line over the entire time range that we're looking at here. So I would say the rate of change at 2002, and you can say instantaneous, is greater than the average rate of change R, because, and we want to explain this graphically, the tangent line at 2002 has a larger or steeper slope than the slope of the secant line from 2001 to 2005. So that is it for this set of notes. If you have any questions, make sure you ask them in class.